And we're going. Okay, so welcome everyone to the first presentation for the Art Show and STEAM Expo for the 2021 academic year. My name is Tyler Sheldon. I'm the Curriculum and STEAM Coordinator at the American School of Asuncion, and I'm joined by some great individuals today. I'm first off joined by our very own Mr. Lipperer, Mr. Nathan Lipperer, amazing science teacher in our middle school. Additionally, I'm joined with his father, Jeff Lipperer. He is here as well to talk to us about engineering design, and so we'll get to that in just a moment, as well as two students, Benha Marcos and Ale P. So for everyone that's joining us, this is a chance where we're going to have community and student presentations for the last couple of weeks of school. These are for fun. These are really for fun. We've done so many hard webinars with the community that at this point, we just want to have some fun and share the cool things that's going on. And so this is our chance to do so. And so we're kicking it off tonight, and it's going to be a lot of fun. And we're starting with engineering design, and we're starting with some 7th grade students, and we're starting with a really cool topic, which is from Jeff Lipperer. So the idea is we're going to look a little bit at some technical design. We're joined by Jeff Lipperer, who's a project manager from a US-based structural engineering firm. And we're just gonna kind of go into the skeletons of some buildings, talk about designs, talk about bridges, talk about mechanical hands, and just talk about the fun stuff. So maybe Jeff, if you wanna take over and just briefly introduce yourself, and then we'll just kind of have our conversation.
All right.
And then if you wanna screen share, you can just take over at any point.
Very good. I'm with a company called Fourth Dimension Design. We're an outsourcing engineering firm. We have 6 engineers that are physical engineers and structural engineers. We tend to work on large building projects, be it shopping malls, schools, factories, churches, that type of thing. We have 2 different levels. We have the conventional structure, which works with the heavy steel, mill rolled steel, and then metal building structures, which tend to use plate steel that is cut from flat plate and then welded together to form I-beams and what have you. So I will start out with.
Let's see, I'm still sharing.
I can't start.
Yeah. I'll pause. There you go. You should be able to now.
Okay.
Yeah, there we go. Just changing the settings. Great. Good to go.
All right. This is a building that we did a couple years ago. It's a multi-building building. As you can see, there's an open entry that's covered. Then you have a little vestibule that's a covered entry that opens up into the office space where I have my arrow pointed now. Where this is for a county, which is a smaller unit of government within a state up in the United States. This one happens to be Washington County, and this is their road building organization, and it's a building that we designed and built for them. So this structure here that I have the arrow on is the office area where secretaries and the administrators and stuff would work from day to day. And the larger building then behind is the shop where the trucks would be parked for the daytime or at night, or whenever they're not being used. And that you can see has a covered section that's closed with the doors for the trucks to go in, but then it also has what we call a lean-to. It's just a covered porch that has the support beam or support columns with the roof over it so that they can get in and out of the trucks without it getting rained on or snowed on. So this is a conceptual drawing done by an architect that then gives the job to our engineers. They determine what the loading is on the building and things like that. And then they will design the building based on what the architect's concept is. A couple things just to look at real quick is you can see how the roof panels have little ridges. You can see little bumps there. Let me see if I can get that zoomed in a little further. Nah, it doesn't look like it.
Make them out a little bit, it looks like
yeah,
ridges.
you can see. And then you can see that this panel, there's lines in it. That's rolls in the panel to give it strength, run horizontally, where the taller building, you can kind of lightly see that the panels are vertical. The rolled lines are vertical. It's just what the architect wanted for a look. So that is the building concept that we get. You know, we're told that the building is going to be this long, that wide, and it has this much wind, this much snow. And so then the engineers move on from there, and they will design this. And this is an anchor bolt plan for the building. And
So I
unfortunately,
guess we're looking at the same building, right? We have like the entryway there on the left.
Yep.
Is that right?
yep,
That kind of mezzanine, or that foyer?
this is the entryway that's covered but open. Then here's the covered entryway. Here's our office space. And then here's our shop. And then here are those columns that are exposed to the weather, where you'd have the overhang that we call the lean-to that's covered. Now, unfortunately, I'm not getting, here we go. So if we
There we go.
zoom in,
Mhm.
you can see that wherever there's columns, there's a letter. This column has a P, here's a T and R. So this entire foundation plan is designed for the people that are going to do the concrete, so they know how big it has to be. Here's the overall size of the building. 248 feet, 7 inches by 101 feet, 1.5 inches. With all the holes, or all the anchor bolts. Whoops. So we go from that.
So this is the one we're looking at right now. This is a foundation plan.
This is a foundation plan. This is the pillars for your bridges. You know, that the structure would sit on.
Mm.
So then we take those letters and we blow it up so that the guys out in the field can see it. And this gives them a close-up of those anchor bolts. So here's, yeah.
So each one of these is a schematic for the anchor bolt and the foundation?
Yes. Yes.
Wow, that's really technical then. So it looks like you have to have clear instructions for each one for the, more or less, the contractor.
Yes, the concrete contractor. So you can see these anchor bolts at M are 5/8 inch diameter bolts, where N, they're 3/4 inch diameter bolts. Again, that's all based on what loads the engineer has put into the building, what he requires, or what the building requires based on the loads. I mean, you can have 1 inch diameter bolts, you could have 1.25 inch, you know, you could have 3 inch diameter, especially if you're working on a big bridge like you guys design. You'd have huge anchor bolts going into those piers. And even though this building doesn't look, you know, if I go back, even though this building doesn't look like yours at all, when it comes to your bridge, it's really just a bridge turned upside down. All the same forces apply. It's just the columns, like, I'm sorry, who designed the bridge?
All of the students did in the class, but Ben Ha's going to be the one sharing it out.
Well, so the columns that support your cables are the same as the columns that are supporting what we call rafters. And the rafters would really be what your deck is. So it's just the bridge turned upside down. And so the force of gravity is still pulling down. It's compressing the rafters instead of compressing the deck.
So that's a good question. This year, obviously this year was virtual, right? And so we didn't have as much time as we would be able to go into all of our subjects. It was just curse of the pandemic year. But we did look at a couple things. We did look at tension and compression forces, like you were just talking about right now. And then we did look at basic material strengths. Benha, do you remember when we had the conversation about material strengths? We looked at, I think we looked at steel, and then we looked at concrete. Do you remember that discussion that we had a while back? We had some models that we looked at.
Actually, I don't remember. I don't remember.
No,
No.
too far ago.
Yes.
But we looked at just the basic materials of steel, concrete, and then reinforced steel. And you've been talking, Mr. Lipper, about some other more complex materials, it sounds like. So yeah, this is all really interesting. Thank you so much for sharing this at this point.
Just to give you an idea, let's do this. I have to move you back over here. When I say plate steel versus factory rolled steel, this is a column that's part of this building.
Okay.
There you go.
There we go. Yeah, it looks good now.
So this is the column that is going to support the rafter, and down in the bottom left corner here is all the steel that's going to go in, and this is all rolled plate steel, but it's flat. It's not a W shape that you might probably used in your bridge construction. In this case, it's all going to come in flat plates, and then it'll be cut by a plasma machine or sheared. Back in the old days when I first started doing this, it would be sheared, but now it's all cut with plasma cutters. And what I do and the people in the office that are detailers like myself, we are taking what the engineer does, coming up with the model for the bridge, or coming up with the formulas and the plate sizes for a building. We're going to then generate parts like this. The drawings that I'll show you in a little bit are what go to the field for the erector, so he knows where. In this case, the bottom right corner down here, where'd my cursor go? There it is. This is called RF1-303.
Are you able to zoom in on that a little bit?
Let me.
Yeah, the full screen and then this one. There we go. Yeah.
There you go.
Oops. For some reason, it's not shifting left and right for me.
You have the scroll bar on the bottom. It's kind of faint there, though.
Oh, there we go. Yeah.
Yeah.
Okay.
There it is. Yeah. Perfect.
So this column's number is RF1-303. So that's going to tell the people in the field where it's going to go on the erection drawings. But this goes to the shop. This is what the shop's going to use. It's going to weld all these different pieces to the column at the locations that we've listed, with the material sizes that we show in what we call the bill of materials over here. So the WBs are the webs that, again, would be cut by a plasma machine out of a piece of flat steel plate. Then it's going to have the OFs are the outside flanges, the IFs are the inside flanges. Then the other things are, like the EP300 is the base plate, which is going to connect to those anchor bolts that I showed you. And the EP301 is the plate that will connect to what we call rafters.
A lot of this looks like Legos for adults. Like we're getting the instructions and we're getting the this is how you build it together, because a lot of these instructions look kind of similar to a Lego book. Sometimes it just gives you a number and some diagrams, and you kind of you make sense.
This piece fits with this one. Find piece or block A, B, and connect it to block A, C, or something like that.
Yeah,
and that's a very accurate analogy. That's really, when it comes down to it, that's what it is. And the bridges, or the hand that you design, if you were going to have somebody build it for you, you would have to have somebody like myself, a detailer, that would take your engineering design, because you're going to be making lots more money than I do you don't want to take time to make these drawings. That's for somebody like myself, that then this will go to a shop where they will cut the plate and weld it together before it gets out into the field to be bolted up. So along with this part, to give them, the shop, a better idea, because we have the lengths, if I can go back over, and the sizes of all this stuff, but it doesn't really tell you what these webs look like, because they're not perfectly square, they're angular. So we generate what we call a web sheet as well. And that web sheet then are those parts with dimensions. So again, they know what to do with how the plasma machine needs to cut those parts so that they'll fit properly into the column.
So they get the instructions on how to cut the materials at the site. So they receive the sheet metal or the rolled sheet at the site, and then they have to use these instructions in the plasma cutter to cut them to spec.
No, this would be done by a web fabricator. These would come fully welded together out in the field. These drawings would go to whoever's going to fabricate them. The construction company maybe has its own fabrication plant, or it might be somebody that they hire out, or it might be somebody that we hire. But this would be done in a factory by a fabricator, and then loaded on flatbed trucks and shipped out to the site. So they're complete units when they get out to the site.
So there's a lot of people involved in this. I mean, you've talked about the architect, you've talked about the engineers, you've talked about the detailers, you've talked about the factories, you've talked about the erectors. Like, this is not just, a couple people putting a building together. This is a very complex process.
Yeah, a building like this, the architect may have it for months or a year to come up with the design that fits within the codes, the building codes for the area. And figures out exactly what the client, in this case, Washington County, wants. Our engineers would take weeks to design. We took about 6 weeks with 2 of us to actually detail the erection drawings and the part drawings. Then you're looking at, depending upon how big the fabricator is, a week and a half to fabricate all the parts. And then just the erection of the skeleton of the building, you're talking a couple months. So it's a multi-month, if not multi-year project from the concept to the completion of the building.
And it looked like that original schematic you had that had the architect's interpretation of the buildings. There was a section on that diagram that said bids or alternative bids. Could you talk maybe just about all the money involved in this?
Sure, let me go back to that.
I have a figure in my mind, and I'm wondering if it's anywhere close or completely too low or too high. I don't know. Ale Pete, how much do you think this whole building costs? Do you want to take a guess? In dollars, if you had to take a guess?
I have no idea. But in the thousands, definitely, yeah. But there was I have no idea.
Benha, what about you? How much do you think this whole building from start to finish, all the individuals involved, all the detailing? It's a government job. Keep that in mind.
I think maybe 200,000.
200,000. How much was your bridge that you built?
600,000.
600,000, right? Okay.
This one, it is a bid set, so this is sent out by the architect, and you can see it's the architect and Washington County would send this out for bids, and in the end, I don't know the exact price of this one. I never saw that, but I would say beginning and end, you're probably looking at 1.2, 1.3 million beginning to end, with landscaping and all the other things that go along with it. Over $1 million for sure, beginning to end.
And in total, about a year, right? It's about a year from start to finish, maybe
Yeah,
more.
minimum of a year, to get all the parts moving, once the decision to go ahead is made. So lots of stuff can happen. Look at what happened last year with COVID, so when somebody plans a building like this, a lot of people have investments in it, and steel prices have gone up because of COVID, trucking costs have gone up because of COVID. All those, I'm sure the architects have raised their price. So there's contracts that are signed and you have to stay within a percentage. And if you're going to be over that percentage, then you have to ask and prove to them why you need to raise your price. There's usually somewhere in the wording of the contract, there's something about steel prices, and the price is guaranteed depending upon how volatile the steel market is at the time. If there's a range, that after 60 days, the price isn't valid anymore. If the steel goes over a certain percentage increase, or it really talks about decreasing. It usually talks about increasing prices. So,
it seems to be all we ever see lately, right?
Yeah.
Jeff, thank you so much. This is a really clear insight into complex design and leaps beyond what we're doing, but giving us a view of where it goes and how what we're doing can connect with the real world. And so if it's all right with you, I think I want to turn it over to Benha and Ale just to share kind of the constructions that they've been making. And then we'll open it up to just general Q&A from Benha, Ale, myself, and Nathan. And then if there's anybody in the any attendees that have questions as well. Is that all right with you?
That's perfect.
Great. So Benha, why don't you go ahead? You can screen share. I believe you can just take over. And
Okay.
yeah, the stage is yours, Benha.
Can you see it?
You can.
Yep.
Yeah.
Okay. So one of the units that we did this year was about bridges. We researched bridges, the type of bridges, materials, the loads, and that stuff. Then we were able to do some bridges. For example, here I made a suspension bridge with like a truss bridge at the deck. That cost me a lot. There were test phase and all that stuff in an app called Bridge Designer 2016. Then I also made a cable stayed bridge that costs $610,000. And then my final design, I tried to make a cheap bridge, right? That it costs and $384,000. This bridge was like a truss bridge, like in a deck, supported by a pier. And what I found, this was one of the more cheapest bridges to make. And as you can see, it looks like successful. Yes.
Was
I
that
like
your
that
most
one.
successful of the three?
And I think all of them were successful, but I think this one was the best because of the cost, and you can see it was pretty stable.
And price-wise, it was the cheapest, correct?
Yes, yes.
With this kind of a program, we found that it's really difficult to get a bridge for about under 300,000. And like, what would add to the cost? Like Benha, what would increase the cost of your bridge? What would make it more expensive?
If I use more expensive materials, it will cost a lot. Also, if I put oversized, and for example, if it is carbon steel and that stuff, if I increase the size, it will cost a lot of more. And yes.
And did we learn anything about the price of steel just now?
Yes.
It changes. It's a volatile market, up and down and up and down. Something that we didn't have to get into. Well, cool, Benha. Thank you so much for sharing this. Let's turn it over to Ali P. If you can take over and show us your mechanical hand that you've been working on for the past few weeks.
Okay. So for the final stage of our STEAM project, we could choose our own project or challenge. And I decided to do a mechanical hand axles. And I chose this idea by first looking for other possible ideas that I could have. And this idea really caught my interest. And this area shows all the materials that I used. For example, straws, threads. I needed to measure everything to make sure that it was accurate to a real finger. And in here it shows how it looks and more images of me creating it, and also trying to hold a water bottle, which it doesn't really work that well because the hand is really weak. It doesn't work as a normal hand since it's made of straws, and the movements aren't really that accurate. They they aren't perfect yet, and yeah.
Those are some really interesting observations you just made, Ale, just to the, now I can't stop looking at the cat on the computer. Can you go back? Can you go back up to the photos? There we go. You said specifically the materials, like the straws. Like you said, the straws really weren't that strong. And then
Yeah.
there's something else you said that I thought was really interesting. So I guess a good question is, Ale, like, how would you make it better? You know, what would you change if you could do it again? If you had money, let's say, Ale, you had a budget,
Oh,
you had
okay,
like,
yeah.
you had like
Yeah.
$1,000. You had $1,000 and you could go buy some better stuff. You know, how would you do it the second time around? Or how would you recommend
Well,
someone to do it?
first off, I would use completely different materials, like not using plastic. To try using more stronger, but at the same time they do have to be flexible. So it can be difficult to know what materials to use. And then you you could also use a stronger thread, or to make the move to make the to maybe make the fingers have more accurate movements. And of course, then there's the hand. You could change the base of the hand to another material that could be more durable.
Yeah. The materials you used are perfect for like a mock-up or like a prototype where they're cheap, they're easy to fabricate. I mean, we're not sending the steel away to a factory to be cut here or using a plasma cutter to cut any of
Yeah.
this steel. We're just using
Wouldn't that
scissors
be
and
neat?
cardboard. Yeah. What sort of application, Ale, do you think this hand could have? You know, how could people use this? How would it make lives better?
Well, this exact prototype wouldn't really work as a prosthetic since you need a hand to make it work. But I think that I do think that prosthetics are extremely useful to humans since the hands are one of the most important things. We can't really do much stuff without it. Like, yeah, it's, um, yeah,
I saw something fascinating the other day. It said that there was a prosthetic for a woman where it added a thumb to the other side of her hand. So she had a thumb on both sides of her hands, and it was connected neurally to her. So she could use her brain to control it. So she could control her normal thumb and then the additional thumb on the side. And the result was that it was kind of useful. It was kind of useful to have an extra thumb on the other side. And it just makes you wonder sometimes, you know, what's possible, what we can make. Well, cool. Well, thank you for sharing, LAP. We're going to take a few moments and just do general questions. So if you guys have any questions for Mr. Lipperer, now's a good chance. I'm going to ask questions too. I'm really interested actually, Mr. Lipperer, like if LAP or Benha, if you have questions, go ahead. Otherwise, I'll just jump in and ask one.
I had one question for Ollie. What did you use to make the fingers, the straws bend? Did you run a cable up through the straw, or because I couldn't from the pictures, I couldn't really see how that you got them to actuate.
I ran the thread through the straws and then tied them to a ring so that they could move well.
Okay, all right. Excellent. Did you pre-bend the straws so that you had weak points in the straw then?
Yep.
Okay, very good, very good.
I wanted to ask a question about weather. You mentioned in the buildings that you work on, you deal with rain and snow. And so snow is something that does not exist here. I don't know if Nathan has talked to you much about the climate, I assume so, but snow is not a big factor for buildings here. So I imagine buildings probably here have different factors entirely. Like if you remove snow, but you had add other things such as like heat or humidity. Are there any other things that you usually have to deal with, like kind of unknown factors that are based upon the location? Like if you're doing a project in a certain location, you have different code you have to follow.
Yeah, obviously soil is a factor. How strong the soil is will determine the foundation, how deep the foundation has to go, especially not the entire foundation isn't the same thickness. Wherever there's columns, you're going to have footings that in northern climates like here, they have to go below 4 feet, below what they consider the frost line. So everywhere you see a column, there's going to be a pillar underneath there that goes down 4 feet. The concrete itself might only be 8 to 10 inches thick for the overall surface of the building, but wherever there's a column, there's going to be a deeper footing. So soil is a factor in that. Obviously, you get out in California, earthquakes are a factor, so they have to increase the foundation and the overall structure. Columns are going to be much heavier, to absorb those earthquake loads. Your storms down there might be stronger than what we get up here, so the wind loads would be higher. And then obviously what's going to be connected to the inside of the building, that's going to play a big factor. Is there a crane inside that's going to move parts around? This building didn't have a crane. It did have a mezzanine, but because it's the part of the building where they're going to store trucks, maybe they would have had a crane in there to pull an engine out of a truck. Well, then that's going to change the load on the building because it's going to have to be able to take the weight of the crane plus whatever the crane's going to pick up. So that would have to thicken and reinforce the structure.
Yeah, a lot of complexity, a lot of complexity.
Yeah.
Ben, LAP, do you guys have any questions?
I have one. You talk about if the soil isn't like firm, what do you have to do? Like you have to put the columns more below the ground or how?
Could you say that one more time, please?
For example, if the soil isn't like firm to support the structure.
Okay, yeah. There's several ways, like a riverbed with the bridge. If you're going to do pillars that are going to go down to the riverbed, they call them caissons, and they'll actually make a structure, drain the water out, and then dig down until they either get to bedrock, where it's solid stone, like a big sheet of granite or something like that. If that isn't available, then they'll drive in a series of what they call pilings, and those are tubes of steel, and they'll have a crane that drops a weight, and they'll just pound those down into the sandy soil, and that then over time they fill that up with however deep the engineer decides and how big a square, so that you're actually not then sitting on the soil, but the soil has tension and suction on that steel, and then that becomes the base. So the soil is super critical, especially for bridges. If you're gonna go down into the canyon or whatever you're crossing, rather than doing the suspension bridges over the top.
Yeah, that's a good point, because your cheapest bridge, your pylon bridge, was having a pillar right in the middle of the water. your bridge that was about $300,000.
Yeah, a bad river bottom would add to the cost.
Thank you.
You bet. Thank you.
Well,
I
I
really-
want to, yeah, go
I
ahead.
really like your designs. I like your bridge designs. They're awesome. That we don't, it's just who we are as a company. We just don't get involved in bridge construction or design. You know, we specialize in the buildings, but I really like what you did. A couple of them were real attractive. The cable stay bridges. I like the one where you had your pillars on the corners and they angled down in rather than having the arched cables. You had the angular cables, so there was nothing in the middle. It reminds me of a bridge. I think it's in Australia that kind of looks like that. Cool design.
Thank you. Thank you.
We're gonna probably bother you again, Jeff, and maybe once we do this project again, we'll reach out to you and we'll get a chance for you to speak to our whole class and just like you know, a little more focused, look at some bridges, give advice if that's all right with you.
I'd love to do it. I'm honored to be a part of this. So
Great, looking forward to it. I'll bother you probably sometime in November. I think that's when, or maybe, when did we make bridges? Was it February? I think it was more recently. Well, cool. Well, I want to thank everybody here. Jeff, thank you so much for taking the time to spend with us. LAP and Benha, you guys are awesome. Thanks for being total champs and sharing your projects. And Nathan, as always,
And a
thank
happy
you for being,
observer here.
yeah, I mean, super supportive. It's always nice to have friends around. Tomorrow night, we are going to be meeting with Francesco Gallerini. This is an ASA grad. He had worked with Giorgio Armani, actually. He has a pretty interesting story to tell. He's back in Paraguay and he's going to be meeting with us. And we'll have our digital design students sharing out some designs and some 3D monuments that they created. Wednesday night, we're going to meet with Claudia Rodriguez. She's going to discuss STEM education and the Ben Franklin Science Corner. It's a leading STEM institution here in Asuncion. Then we're going to hear from a medical doctor. That's going to be on Thursday evening. He's associated with the US Embassy, and he's going to talk about practicing medical science and biology during COVID-19. We'll take Friday off and be back next Monday, where we're going to hear again from 7th graders and their community improvement projects and an actual community improvement organization called ASU Mas B and Sistema B. It's a global organization to improve community development. And then we're going to finish off our community presentations that Tuesday with Dr. Jorge Curita. He's the engineering director of the Paraguayan Space Agency, and we'll learn the story behind their Guarani 1 satellite. So again, our goal here is that you guys design innovative solutions to 21st century challenges through collaboration, communication, and creativity. And Benha and Ali P, you did, and that's awesome. And so we really appreciate everything you've done here. If there's no other comments, I think I'm gonna just close it out and wish everyone a fantastic evening.
well, thank you for letting me be a part of this. I really did enjoy it.
Thank you,
All right.
Mr. Lipperer, and Benhan Ali, great stuff that you guys made. Really cool seeing it.
All right. Have a great evening, everyone. Bye-bye.
Bye. Thank you.
Thank you,
Bye.
guys.
See you guys tomorrow.